Welcome, early birds. Really good to see you here. I'm Callista Redmond, CEO of Risc-V, and I'm super excited to kick off our summit week with all of you. I know Risc-V 101. Some of you in the audience I know are well versed in Risc-V already. So I appreciate you here, and don't feel shy about chiming in with additional little golden nuggets to help all of us on our journey to realizing the Risc-V potential. Yeah, that's me. Welcome to Risc-V 101. And we have a packed agenda today. So I hope that many of you will be here for the full summit this week, but today is really dedicated to accelerating your on-ramp, thinking about how Risc-V applies to you as a person, to you as companies, to you as students, to you as your stakeholder interest in Risc-V. At the end of the day, Risc-V really is about the community that we're building, the collaboration that we're embarking on, and the implementations that are going to market. Some of you may have heard me say this before, but open collaboration, unless it reaches commercialization, is called a hobby. We don't need more hobbies. I can't keep up with the hobbies I've once, imagined, kickboxing, snowboarding. I'm a horrific snowboarder, by the way. Camping, things like that make us human. And Risc-V is a great hobby, but it really starts to gain traction, passion, and dedication of an entire community when we come together on it. So I'm excited that you're here embarking on your journeys. Regardless of where you are in that journey, it's important that we come together and know that this is your family. This is your Risc-V family. Lean on us, talk to us, get to know us, make a lot of new friends, especially if you're here for the week. So we have a lot of great talks today. I'm in charge of welcoming you and introducing the agenda. So John Ronco of Sci-Fi will talk about what is Risc-V in the first place. We've already gotten past the how do you pronounce it part, so we're well on our way. Why Risc-V? Keith Graham of Codicip will talk about why are people making the decisions to go with Risc-V. Risc-V is fundamentally changing the course of history. In fact, we're writing a new history, and this is the first chapter for many, and some are well on their way. The Risc-V ecosystem. Ted Spears of Microchip is really deep in this subject. He's been working over at Microchip on things like PolarFire SoC, which, by the way, is also the Wi-Fi code. And if you need help getting on the Wi-Fi, let us know. But he will talk about, how do you accelerate that developer journey on Risc-V, and what can that mean for you? Where are the tools and resources to make that possible, and how is it growing today? Right, Ted? That's what you're talking about? I just covered a whole bunch of stuff, so I got your back if we need to fill in. Make versus buy on Risc-V with Larry. He's got a great presentation ready to go. And thinking about, do you work with and collaborate with development partners? Do you think about building your own or enacting your own journey? The thing about global open standards is it lays the foundation for you to bring your differentiation on top of and around that. And that really is a powerful thing as you go to compete in the markets, domains, industries, and such, from the smallest, lightest weight processors all the way to robust data center implementations. It's really cool that you can really create your own journey and differentiate. So make versus buy is a compelling discussion there. Software. Jeffro is going to be talking to us about that. He's over at Red Hat today. He was formerly part of the Risc-V staff, so he has a long history with Risc-V, and will bring us lots of compelling information about where that software ecosystem is and how to continue growing that. Getting involved in Risc-V technical communities with Martin Moss over at Google. Realizing and growing your technical skills, engaging in technical work groups to influence and strategically drive the direction that we're taking as an organization, through to specifications and ratifications, engagement, contribution. Maybe you start as a spectator, and maybe you end up as a leader, a chair, or vice chair of a work group. These are important and compelling reasons to show your technical leadership. Build your technical eminence in this community, not just as an individual, but as an organization that you may represent. So a lot of fun stuff intact here for today. I'll be back later today to help us wrap up these sessions, and I'm looking forward to meeting and engaging with any of you and all of you. If you need to reach any of us on staff, pretty easy to find, first name at riscv.org, and looking forward to embarking on the journey together with you. So here we go. It's time to kick it off.
Good morning. It's great to be here. I flew in yesterday from Riga in Latvia, coming from the Ubuntu Summit, so I'm feeling very wide awake at this time of the morning, and I'm going to crash horribly about 4 or 5 o'clock this afternoon, but you've only got me for 30 minutes, so that's okay, so I should last. So my name's John Ronco, so I lead segment marketing at Sci5, and I'm going to talk to you about what is Risc-V. I've actually been involved in the Risc-V ecosystem for about a year at Sci5, but before that I was watching for the sidelines for a very long time because I was at ARM for many, many years, including at one point establishing the competitive strategy team to work out what ARM was going to do about Risc-V. And as the saying goes, if you can't beat them, join them. And so that's why I'm here now. Okay, so what is Risc-V? So fundamentally, Risc-V is an open standard instruction set architecture. Now, the ISA on a chip is super important because this is the interface between hardware and software. And so it's a really critical component of any SoC. All of the legacy ISAs that are out there are proprietary, and they're controlled by a single company. And fundamentally, that's a problem. With the end of Moore's law and the rise in the need to do computing around AI, we're going to need to innovate more and more about how we get performance out of chips, how we get the optimum performance, optimum power, etc. And working with a proprietary ISA is just not going to cut it. So we need a different approach. We need an open standard, and that is what Risc-V is doing. And Risc-V is therefore changing the way that we're going to be building chips for the future. So bit of background, bit of history. Some of you in this room look far too young to remember much of this. I don't even remember some of this. But this is basically a kind of a sort of a history of where instruction sets have been in the computing industry. And you can see that there's some of them have come and go, some of them become popular, some of them become less popular. A number of them have gone through different iterations in terms of who owns them, what the company strategy behind the ISA is. And then some of them have dabbled with being open a little bit, and then sort of undabbled with being open, but none of them have really committed to it. But the key point here really is that you can't depend on an instruction set that is controlled by a single company. I mean, even at the bottom, say something like ARM, which is an instruction set, is relatively open in terms of lots of different companies making chips from it. If you've been dependent on the ARM as an instruction set over the last few years, you've gone on quite a roller coaster with the proposed NVIDIA acquisition, then that being off, and now the IPO, and now being driven by sort of different commercial desires of the company. And so therefore, the key point here is that if you are dependent on an instruction set that is beholden to the whims of one particular corporate entity and its investors, then that can be a challenge. And ultimately, why would you want to bet your future on something proprietary? And it's also worth thinking about what goes into a modern SoC in terms of the number of different cores and number of different processing elements. This example is actually very old, but the situation's got a lot worse since then in terms of being more and more different types of cores that are in there. So even something that might be notionally an ARM-based chip actually has many, many different cores that are not ARM in it. It actually has many different ARM ISAs in it, from like the Cortex-Ms, the Cortex-As, the Cortex-Rs, and the like. But then you have other cores like the GPUs, the TPUs, the DSPs, all these other processing elements, and they all have their own kind of instruction set in terms of how you program them, how you work with them. Now, there's lots of historical reasons why these different ISAs have existed. Some of those are good, some of those are not so good. Some of them were kind of like people just doing things for the sake of doing things, or people doing things because they felt they had to. But the key question is really, do we need them all going forward? And that was really the kind of the founding kind of concept behind Risc-V was do we need all these different ISAs? Should they be proprietary? Why do they keep disappearing? And wouldn't it be better if there was a stable, free, open instruction set that everybody could use for every use case? And that was really the founding principle behind Risc-V. So a bit of history. What has happened? So the first question is why Risc-V? And the simple but disappointingly dull answer is that it was the fifth RISC instruction set that came out of Berkeley University. So Berkeley did a lot of the pioneering work around RISC computing in the early 80s. So Dave Patterson of Patterson and Hennessy fame, or Hennessy and Patterson, depending on which book you read, did a lot of the initial work in the 80s, and they did several iterations of different RISC instruction sets that they worked with. And then for a couple of decades, they generally relied on commercial instruction sets to do the work that they were doing. But around about in 2010, they decided that that wasn't going to cut it anymore, and they needed to do something new. And so they decided, so a group of four of them, so Dave with Andrew, Yunsep and Krista, decided that they would develop a clean sheet ISA as a summer project to help them with some of the research that they were doing. And then once they did that, they then realized the potential that this would have as an open standard that could be used across the whole of the industry, could be used across all of academia, across all of industry, and basically any use case for an instruction set. And so having realized that potential, they decided to launch it on the world. And that led to, in 2014 at Hot Chips, Risc-V being announced to the world, and declaring its goal to basically be a single instruction set that could be used for any computing purpose going forward in any market, in any use case. So a nice modest ambition to start with. But really the point here is because it's open, you can do anything with it. And that was really what the founders were trying to achieve. And it's steadily built momentum ever since. And actually, over the last couple of years, we've seen a real explosion in engagement from across the whole of the semiconductor industry. So anyone who's involved with building chips or building software is really starting to take notice of Risc-V. And there's a huge increase in momentum over the last couple of years. Then just a quick note here on Risc-V International. So once they decided to make the Risc-V an open standard instruction set, the team said, right, okay, we need an entity for that. And then Risc-V International was created, and Callista, who was just talking, obviously runs that. And Risc-V International is essentially the neutral, non-profit, member-driven organization that is responsible for managing the standard and basically making sure, basically setting the standard, helping get the members come together to drive the direction it needs to go in, and then ultimately being the custodian of that. Once they publish that, you're then able to do with it what you like because it's an open standard, and that's obviously part of the key benefits. Risc-V International also do a lot of work in terms of growing the communities, working with members, running events like this. So really, they're kind of like the standard bearers for Risc-V in the wider world across all the different use cases. So that's the history, that's the background. That brings us kind of like where we are today. So I guess the question is why? Why is Risc-V gaining this momentum over the last couple of years? Why are all the big semiconductor players and everyone who's in this industry is really starting to take notice of Risc-V? Now, at this point, I may risk offending some of my engineering colleagues because a lot of them will claim that how Risc-V is better than other ISAs and it does certain things in different ways and that leads to certain improvements in what you can achieve. And actually, all those things may well be true. And are true in many cases. But really, the fundamental reasons that Risc-V is getting popular is the business model, is the open standard. It's the freedom to do what you like with it, and the fact that you can use that in every use case, whether that's industry, whether that's academia, whether it's high-end supercomputers, low-end microcontrollers, whatever you're trying to do, there is an applicability to use case. But because of the business model, because of the open standard, you can invest in confidence in what you're doing, you can invest in software with confidence, and that you know that you can have a long-term future with it. So the technical benefits of Risc-V are important, and clearly as a community we should strive to be best in class for every possible use case of Risc-V, and there's a lot of work going on to make sure that is happening. But ultimately the inevitability of Risc-V success, in my view, is due to the nature of the business model, the nature of the open standard in terms of what it offers. So looking a little bit more closely at something around that. So open interfaces in computer science are pretty much accepted. So in a lot of these fields, you can see there were originally some proprietary standards that were being set and that were being managed, and eventually they're being replaced by open standards. And these open standards allow for open source implementations of the standard, but they also allow for commercial implementations based off the open standard. But the general principle of open standards for interfaces has become widely accepted across the industry. And the question is, why should the instruction set be any different? The instruction set is just the interface between the hardware and software on a chip. And the simple answer is it shouldn't. It really shouldn't be. So that the benefit of having an open standard for the ISA applies just like the benefit of having an open standard in any other interface. And so if we take three of the most popular ISAs and look at, well, what does this mean? What does this open standard mean in terms of the business model? Then with the x86 instruction set, you can get x86 chips from a couple of different vendors, and that's good, but it's not great. It's fairly limited in terms of what you can buy. And if you want to design your own x86 CPUs, you can't do that. If you want to build your own chips using x86 cores, you can't do that. If you want to change anything, you want to add your own instructions, then you definitely can't do that. And you certainly can't have an open source CPU based off the x86 instruction set. So it's not great. Now, ARM is a bit better in the sense that because the way ARM does its business model, it licenses CPUs to chip vendors. There are many, many different chip vendors who are building chips that are compatible with ARM and that you can run ARM software on. So that's a real positive. But if you want to actually design your own CPU, that's possible, but it's very expensive. And it's also quite restrictive, as Qualcomm's found out over the last couple of quarters in their lawsuit with ARM, is that you don't have full control over that. So yes, you can build your own CPUs, but ultimately you're not free to do what you like. And if you want to build a chip to incorporate ARM CPUs, then you can, but you can only buy a CPU from ARM. So if you don't like what ARM is providing to you, then you've got a problem. You haven't got any alternatives. There's not really any possibility to add their own instructions. There is a little bit around the Cortex-M that you can do, and there's certainly no possibility to do an open source core. But Risc-V, on the other hand, you can do all of these things. So Risc-V, there are and there will be many different vendors providing chips that support Risc-V. By definition, because it's an open standard, the architecture license is free, and it's completely free both in terms of cost, but also in terms of freedom, in terms of you can do whatever you like with it. And if you want to buy a commercial core, if you want to build a chip and you want to just license in a CPU for a particular purpose, then there's multiple different vendors, Sci-Fi included, who will happily sell you a high quality production grade CPU. You can add your own instructions, and if you want to do an open source CPU, as many people have done, then you can do that as well. So basically, Risc-V as an open standard gives you the freedom that the existing proprietary legacy ISAs don't give you. So a quick word on Sci-Fi. So as I say, I'm from Sci-Fi. So the three of the guys who founded Risc-V, once they'd handed off the Risc-V instruction set to Risc-V International, decided to set up a company, and that was Sci-Fi. And that was a company which was the goal was to basically build commercial implementations of Risc-V CPUs. And that's who we are. So today we're the largest vendor of Risc-V CPUs, we've got the broadest portfolio, and everything else. Our business model is essentially the same as ARM's, in the sense of if you want to build a chip, you can come to us and we can license you a CPU. But the critical difference is if you don't like what we're giving you, you can go to someone else and get another Risc-V CPU that's compatible with your software in a way that you can't do with ARM. And that's the fundamental difference, again, about Risc-V. From a sci-fi point of view, we announced a couple of weeks ago we've had more than 350 design wins. And so that's with a lot of different major vendors. So Qualcomm, Intel, Google, Samsung, Renesas, Microchip, and a whole ton of other chip vendors globally are using our designs. So that's Sci-5. So back to Risc-V, then the growth of Risc-V is really phenomenal, both in terms of what has happened and in terms of what is going to happen over the next few years. So this is data that is actually, I think, a little bit out of date, and I believe RVI are going to be publishing some updated. Yes, Tiffany's nodding at me. There's going to be some updated data on this in the keynotes, I think, later this week, probably tomorrow. But the key thing is not so much the precise number, but just the scale of the growth. So there's already tens of billions of CPUs have already shipped using Risc-V. So actually, if anything, this is quite a conservative estimate, because a lot of people are using Risc-V and they don't have to report it to anyone because it's an open standard. So a lot of people are using Risc-V in embedded cores that you don't even know about, and that's driving up the numbers. And in fact, almost certainly all of you are using Risc-V already, and you may not even know it. So if any of you have a phone that uses a Snapdragon processor from Qualcomm from the last couple of years, that has Risc-V processors in it. The main processor is obviously the ARM processor still, but a lot of the system processors and other processors on the SoC are Risc-V. And basically a wide range of different kind of embedded use cases have already moved to Risc-V. And as I say, tens of billions of CPUs have already shipped in commercial devices. And from my point of view, what's really exciting is we're just entering that phase where more and more of the kind of user programmable CPUs will become Risc-V. So whether that's an apps processor running Android or Linux or a microcontroller, a lot of these things are now moving towards Risc-V. In terms of the rest of the growth, all of the standard educational textbooks have now moved to Risc-V, and Risc-V is now kind of the de facto standard in education. And this matters in terms of having new graduates having a bias towards Risc-V, which is great. And the software ecosystem is growing really fast. Bits of software that didn't have Risc-V support have started to have that over the last couple of years. And software that already had support, that support has been maturing and optimized and is getting a lot better. And this is, this chart, there's a lot on there, so I'm not expecting you to take it all in. It's just a flavor of some of the things that are happening. But it's a mix of open source software and commercial software, and really just illustrates the momentum behind the software ecosystem that we now have. As I'm sure a lot of you know, these things are a marathon and not a sprint. The software gap between Risc-V and other ISAs doesn't get closed overnight, but it's closed really rapidly over the last couple of years and will continue to close. And on that note, I wanted to talk a little bit about RISE. So Jeff Rowe later, I think, is doing a talk to talk about this in more detail. But RISE is an organization that we established earlier this year with the specific goal of accelerating the development of open source software on Risc-V and commercial open source software on Risc-V. And I think what's interesting about this is that this isn't just what you might consider the vested interests of the Sci-Fivs, the Revoses, and the Ventanas, who clearly are very vested interested in getting software working on Risc-V. It's the Googles, the Intels, the Qualcomms, the Samsungs, the MediaTeks, the Nvidias, the big companies who are saying, actually, we see a significant part of our future is going to be Risc-V based, and we now want to really step it up in terms of what we're doing and make sure that the software ecosystem is ready for commercial deployment. And I think that's probably another important point to say about RISE, is that we're very focused on open source software for commercial deployment on Linux capable type devices. Risc-V International, by definition, has to be incredibly broad in terms of servicing all the different users of Risc-V, from supercomputers to tiny microcontrollers, from academia to industry, so everyone who's wanting to engage with Risc-V. Whereas RISE is very much saying, okay, how do we deploy Risc-V in high-performance compute, whether in mobile or automotive or infrastructure, that's using Linux and Linux stacks basically on top of it. And so it's a really exciting development. The way we're doing it is through a combination of alignment between the members, but also putting in targeted investment to specific projects that need it. And I think to be really clear as well, RISE is not developing any new software. We are very much working with the existing open source communities to make sure that they support Risc-V and can support Risc-V fully, rather than trying to create new distributions or new software. So this is a really exciting development. And then, I didn't realize this had a build. One thing I wanted to highlight in particular was Android, as I think this is a really exciting development in Risc-V over the last year. So Lars from Google stood up at the Risc-V Summit a year ago and committed to making Risc-V a first-class citizen on Android. I'm not sure everyone believed him when he said that he was going to do it. But they have done it, and they are very much on track for making what they originally promised, which was Android 15 next year, the release next year, as having full support for Risc-V. And a couple of weeks ago, Qualcomm and Google did a press release where they were talking about their commitment to make wearables using Risc-V, so Wear OS type devices. And that's really great to see that commitment. And I think the key thing here is that where Android AOSP, the Android open source project, is the same across all the different Android form factors. So if we get it optimized for wearable devices and get wearable devices in the field, then there's really nothing to stop it being deployed across all the other use cases of Android. So this is a really exciting development. So one of the things I want to talk about, one of the great things about Risc-V is the freedom to innovate. So the fact that you can have all these different instruction sets, you can create your own instruction sets if you want, and you can do lots of different things. Now, one of the things at this point the detractors of Risc-V will say, aha, that means that you're going to have a big fragmentation problem. So you're going to have everyone doing something completely different. It's going to be chaos. Software's never going to run on it, and it's all a disaster. Now, that's not true, and I can explain why. But before we get onto that, we need to kind of explain the difference between fragmentation and diversity. So fragmentation is doing the same thing in different ways. So the fact that we in the UK drive on the left-hand side of the road, and everyone else doesn't, almost everyone else doesn't. There's a few other people that drive on the same side as us. That doesn't help anyone. Do you know what I mean? It makes vehicle manufacturers' lives a bit more confusing, a bit more difficult. It confuses tourists in terms of what they're doing. The world would be a lot better if everyone drove on the same side of the road. So in the same way with instruction sets, it doesn't help anyone if people come up with different ways of doing vector processing. So there should be a single way of encoding vector instructions in Risc-V that everyone uses. And that's really bad. The key thing with fragmentation is to avoid doing the same thing in different ways. But diversity is different. So the Boeing 747 and the bicycle are both transportation devices, and both are really important in different ways. But they both solve very different purposes. And the same is true of instruction sets. So you have 64-bit and 32-bit instruction sets. And even within 64-bit, you have those that are designed more for real-time microprocessors and those that are designed for high-end Linux-capable devices. And it makes perfect sense to have those differences. You don't need everyone to do exactly the same thing, but you need to make sure that you're doing the appropriate instruction set for the different use cases. And so diversity is really important. And you see diversity in the existing instruction sets, whether that's from x86 or from ARM or from anyone else. So diversity is really important, but fragmentation is bad. But with all the different instruction sets, you still have the possibility of fragmentation. So how do we avoid the fragmentation? So really, there's two key things that keep fragmentation at bay. Firstly, nobody wants it. So the users really want to avoid any kind of vendor lock-in or any kind of restriction that says, okay, they can run software only on this flavor of Risc-V CPUs. So Sci5 as a Risc-V CPU vendor, we could come up with some clever way of doing matrix instructions and keep it as proprietary and say it's only ever a Sci5 thing. But our users won't want it. Our customers won't want that because they'll say to us, no, we want something that is only standard. And secondly, from a software point of view, nobody can afford to develop their own software stack entirety. So we need to collaborate on that. And the open source software communities are quite rightly only accepting ratified complete standards from Risc-V and are not trying to support special instructions from different vendors. So if everyone focuses on just supporting the ratified standards, then a lot of fragmentation can be avoided. Now, you still have a bit of a problem in terms of just the number of different extensions that are possible with Risc-V, and the fact that you can have all of those and you could combine those in many different ways. You actually lead to a very large combination space in terms of the number of different options that you have. And that's great for some use cases. So if you're doing a deeply embedded processor, or you're doing a very specialist processor, you probably want to have that flexibility to choose exactly what you want. And I think the next speaker will talk a little bit about that, because that's clearly part of what CodaSIP does. But if you're wanting to do a Linux distribution, you really want all of the different Risc-V CPUs from the different vendors and the chips from the different vendors to be the same. You don't want to be having them as all completely random and different. And so that's where the profiles come in. So what we are doing with the profiles is basically packaging specific sets of ISA instructions together, ISA extensions together, and saying, right, okay, that is a set of mandatory instructions that everyone is expected to support for a particular use case, and then a limited set of optional instructions that can be added on top. And so for Linux distributions, it's the RVA profile. And so RVA 20 was published a couple of years ago, RVA 22 last year, and we're just in the process of trying to ratify RVA 23 as the next generation. And I mentioned Android on the previous slide. Android, Google have said very clearly that for Android devices, they expect RVA 22 plus vectors plus vector crypto. So it's a very specific set of looking at the profiles and saying that is what you need if you're going to support an Android device. And we're not going to support Android on lots of older devices that don't support this. So this is a kind of way of kind of keeping the ecosystem together and focused. So that's the profiles. But then actually the ISA by itself isn't enough. If you're, as I say, if you're building a Linux distribution, you would like certain non-differentiating things like how interrupts work, how the boot flow works, to just be the same. You want things like that to just be there and consistent. And that's what we're working on with platform standards. So if you're familiar with what ARM has done around System Ready and SBSA, this is essentially the same thing, but looking at it from a Risc-V point of view. The ultimate goal here is just to make software really boring and work and just run out of the box, so you don't have to do lots of work to port software between different platforms. So that's ultimately the goal of the platform standards. And then I won't dwell on this just in terms of instructions, but just give you a flavor of some of the instructions that have been ratified in 2023. The main thing really, I think, to just take away from this is that, one, there's a lot of things happening. So there's a lot of instructions are being ratified. But also the completeness of the ISA is now pretty good. It's actually pretty comparable to the legacy ISAs that are out there in terms of some of the instructions and some of the capabilities that there are. There's more to be done for sure, but there's an awful lot of, you can now build really capable Risc-V CPUs for any market with what's been ratified. Okay, so to conclude really, so Risc-V has huge momentum and it's, in my mind, is very much now unstoppable. It will have the best processors, it will have the best ecosystem. I think that is now inevitable. And the inevitability is not just because of the technical superiority, although there is some of that, but it's fundamentally down to the business model. And it's a business model that is wanted by all of the major players across the semiconductor industry. And that is fundamentally what is driving the growth of Risc-V and what is going to make the next few years incredibly exciting. So thank you very much. Do we straight to the next person, or any questions, or any questions? Yeah, questions. Yeah, I mean, I think it's, yeah, I think that's true. I mean, I think there's a lot of work that needs to happen in terms of software, hardware, co-design to get the best out of it. But I think that your key point, and this is the reason why a lot of companies have embraced open standards and open source, is that there's a lot of stuff that just needs to be there. And they don't want to invest in that themselves. They want to focus higher up the stack. And I think you're right. I think that is part of what's driving the momentum behind Risc-V. In terms of the decision making within risk, yeah, I mean, I think inevitably there are some louder voices within the standard setting bodies in terms of how Risc-V is driven forward, but it's more democratic in terms of it's across a range of different companies that are working together. And I think that's okay, actually. I think you want, do you know what I mean? The biggest companies with the biggest vested interests, you want to be driving a lot of this. But also, because the freedom is there to innovate, if people want to do something slightly different and prove out a different way of doing things, then there's the opportunity to do that and then steer the community in that direction. And you can see that happening with the way things that have happened over the last couple of years. Different people are coming with different ideas, and it's moved beyond just being a couple of people saying, right, this is the instruction set, to other companies proposing things, and that's what's really exciting. Okay, well, maybe one more question if anyone's got it, or no? Oh yeah. I think it's both. So the question was, is it general purpose computing or purpose built? And I think it's both. So I think if you're doing something very specific, so you're designing it for a specific purpose, the fact that you have massive amounts of freedom to innovate around the CPU, around instructions and what you do, makes Risc-V absolutely ideal for that. But for general purpose, the fact that different people can build different CPUs that are suitable for that can support the same instruction set and support the same platform standards mean that you're ultimately going to get better chips, and you're ultimately going to get better systems to support general purpose software as well. So I think what you've seen so far with Risc-V is Risc-V has gained a lot of momentum around maybe more deeply embedded and maybe more single purpose use cases. But I think that's just the foundation. As I say, we're now at the point where we're starting to see more designs moving into the general purpose space, and that's what's going to be really exciting over the next couple of years. Cool, thank you. Oh, sorry.
Hello, everyone. I'm Keith Graham. I'm the Vice President of the University Program and Customer Experience at Codicip. And my experience is pretty wide. I actually was in industry. So I've actually seen the trend of custom compute, or everyone was doing their own processor, to our, where we went to very few architectures, and now the growth of Risc-V. And I've also taught at the University of Colorado. So as a teaching professor, one thing I like to get my class is to actually ask questions during my lecture. And so I want you to ask questions, and I actually do have questions for you throughout my presentation, so I would like to get some interaction going. My first Risc-V summit was 6 years ago. And at that summit, it was actually at Western Digital. And it was very much, get back to what Callista was saying, it was very much, I would say, a hobby or a research, right? Almost every presentation was on a university working with another university doing research on some type of computer architecture, and maybe with collaboration with some company. But it was basically very much of a university summit until Western Digital came and spoke. So Martin Fink, who was the Western Digital CTO at that time, basically made the announcement that Western Digital was moving towards Risc-V. And that was a big announcement, because that really started the transition from the academic research of Risc-V into commercialization. Then I took off, and I hadn't attended a Risc-V summit for many years until last year. I was really impressed, because now, when I was there last year, there's so many companies now doing the presentations. It's no longer just in the realm of research. So this was really a big event about 6 years ago, when Western Digital was the first major company that made a stake that said, we are going Risc-V, and not just Risc-V, we're going to take what we learn in Risc-V and put it back into the community. And that's the advantage of an open standard type of community. Now, I have a few questions. So once again, my presentation is why Risc-V. So I did a little research last week. And so what is expected when you look at IoT, Internet of Things, and AI? What do you think is the revenue expected for 2022? Actually, it wasn't expected. This was actually done. So any idea out there? 3.1 billion we have? I feel like an auctioneer now. 3.1 billion. Any other ones? 10 billion. So 10 billion. Okay, so $10 billion was in 2022 in AI for IoT. Now, what do you think it is in 2028? We got 6 billion. We got 6 billion. Any other bidders? What's that? 50 billion. Anyone else? Well, we're going to have to go with 50 billion because you're the closest, but it's still pretty way off. It's 92 billion. So we're looking at a phenomenal growth in AI IoT. Now let's take a look at DSPs 2023. It's a little bit older technology. It's not really like AI, which is everyone is focusing a lot of research and development on. But what do you think DSP revenue was forecasted in 2023? We got 10 billion? Now, it's one of those things, if I see you like do this, I'm going to call you and figure out how much you bet on. So it is actually 5 billion this year. So what do you think is the DSP revenue expected for 2029? We got 100 billion? We got 100 billion? What's that? 7? 7, you're the closest one. It's actually 6.6 billion. That's a really nice number there. So my big question is, when we look at these markets, we got AI, Internet of Things, and we got DSP. Now, what differentiates these markets from the general purpose processor or microcontrollers?
Can we be careful? Are we talking about AI as an ML, or are we talking about AI as an AI?
When I came up with the focus on the revenue, it just said AI. It didn't specify AI or ML specific. It just said AI. So I apologize. I can't be more specific on that. So what differentiates these potential revenue streams compared to the general purpose markets or microcontrollers? Power consumption is one, especially IoT, right? A lot of those are batteries, so it's very much low energy. Anything else? Size. Size is related to cost, and also size is somewhat related to power as well as the end product is normally small. Anything else? Security, yes, because you're you're broken from the barrier, right? You're not in a closed computer room anymore, right? So you're in the wild. Anything else? It could be vector processing depending upon your application, correct?
I think it's both the amount of data being handled as well as capability for parallelization.
Correct. There's also a really nice balance on IoT specifically. You know, how much you want to actually do local versus in the cloud, because there's your bandwidth to the internet and so forth. So in essence, each application has a different set of requirements, right? You think, we just talked about a lot of different responses of what differentiates it. It really depends on what your application is, right? Where when you think of a general purpose processor that goes in your notebook, well, most notebooks have the same type of requirements, right? Most, say, Linux operating systems, we're talking about different platforms, right? So that you can run that Linux on whatever platform, right? So they have a much more common set of requirements. So when you take a look at these particular markets, which actually have large dollars, large growth, require differentiation. Now, we're going to go back in time. So actually, I worked for this company down here called Solborn. We were doing a custom processor back in the 87. And so back in 87, it was probably about 89, Sun Microsystems came to us and said, no one's going to buy your custom processor, right? As a startup, you don't like to hear that, right? But they were right. And what they said was, software is going to be more important than hardware, right? And at that time, everyone was doing their own processor. I mean, I worked at Hewlett-Packard, Sun Microsystems, all those companies were doing the custom processors. And unless your company can guarantee a hardware platform for at least 10 years, no one's going to port their software to your base, your processor. So they convinced us, and Solborn became the very first Sun-compatible processor in the world. So we switched over and we did a Spark-compatible processor. And so then we entered the 90s. Some of those architectures ended up dying, and we focused on more x86 and ARM were the big players, but MIPS was there as well. And so when I started teaching at the University of Colorado in the mid-2010s, I had some students ask me, I'd like to be a processor engineer. And I go, well, I don't mind helping you learn how to do that, but there's not a lot of companies to work for, unless you want to work for like Intel, ARM, AMD, NVIDIA. There's just a small handful. But what I think we're going to be seeing here is what I call the next golden age of processor engineering. And it's being driven by all these different products that need differentiation, right? We got EVs, we got drones, we got space, robotics, even commercial products, consumer products, right? All these different products are going to create a need for differentiation. And it's been really amazing to think that there's a lot of software companies out there that you think are software companies, but they are a very large spender of hardware. Because they understand that differentiation is not always software anymore, but it is how well your software runs, particularly how well does it run in the cloud. So there's a lot of customization in hardware, and what we're going to be seeing is this strong demand for unique processing capabilities out there, which is custom compute. The nice thing about this is as long as you're Risc-V and you add resources and not take resources away from your processor, you can still run the base software that's available in the Risc-V ecosystem, but anything that's compiled specifically for your processor will get the benefits of that particular architecture. Now, I used to, this is a few slides that I would start my classes with in computer architecture, was I really like pizza. If anyone knows me, I have a lot of stories on pizza. And if I want to make 16 ounces of pizza sauce, in the United States, it's a little difficult because my choice of cans of tomato sauce are 8, 15, and 28 ounces, right? But I want 16 ounces of pizza sauce. So how do I do that? Well, I could use 1 can of 28, 2 cans of 15, which I have a lot of leftover tomato sauce, or 2 8s. But 2 8s, like 2 cores at 8 is not always the same single thread processing as a single 16 ounces of tomato sauce. So the idea is, can we take a smaller can of tomato sauce or processor and then add the functionality or resources to make it equal to 16? Now the beauty about going from the smaller to larger, I can actually specialize it for my particular application. So now my 16 ounces is not just tomato sauce, but it's actually pizza sauce. So by specializing, you can actually provide additional value to your in market. And the thing is, if I start with a smaller core, a lot of times I can actually have a less expensive solution as well. So there's a lot of advantages of going small and up. CODASIP has a few white papers where we show where someone's taken a small core and through custom compute has actually enhanced the performance dramatically for their particular end market. Now, there's always a potential need that you need a lot of pizza sauce. So I actually have this for my spaghetti when I make spaghetti. That's a lot of sauce. But you might have a need for actually something completely custom. And the thing is, Risc-V allows you to do that as well. Now, let's take a look at what if I do not do custom compute, right? Remember I said that I might have to go with a larger can of tomato sauce for what I need. Now, if I pour that can, or if I look at this 16 ounces is a lot smaller than my, say, 28 ounce can of tomato sauce, right? So if I look at that area compared to if I bought an off-the-shelf processor that had the type of resources I need, I get what I call IP leftovers, right? The leftovers is a larger area, which is related to cost. A lot of times more power, which is related to greater energy usage. So there's a lot of additional costs that you are paying for if you take a standard compute for these particular marketplaces. Now, you need some more reasons, right? That's a great reason, right? And when you look at companies, there's a lot of different levels of management when they decide on what processor or a key technology to choose on. right? The low-level engineers have to validate that it technically will work, right? It has to work. Then you go up the management chain, and there's a manager there that needs to ensure that the product's going to release on time and on schedule. And then when you go all the way up to the vice president normally is responsible for increased profit. So these are all decisions that have to go hand in hand. Now, the last slide was talking about how you can actually ensure that you have the best feature set for the product. But now let's take a look at that next level of management, because that's another thing, person you have to discuss about why Risc-V. Now, this is actually a real customer experience that I know. So they designed they spent 2 years designing a SoC with an ARM chip. And when they started the project, they tried to figure out what was the right size core for my application. So they started the development, they chose the core, and they finally got their first silicon back. And they realized that the software over the 2 years bloated so bad that when they actually got the silicon, now they can't meet the specification requirements of the application to actually sell the product, right? That is a big risk management issue. Now the question is, if I have this example where I have to go from 16 to 20 ounces, if I have a closed architecture, I can't do anything about it. If I want to go make the change from, say, one class of ARM or a proprietary processor to another, that's a big change potentially to your layout and design. Where on the other hand, if I use Risc-V, I can go and figure out what are the new dedicated resources and do an incremental change to my design to enable me to continue with my current SoC. I might have to spin my ASIC again, but now I'm doing a minor change and not a major change. So I really believe that Risc-V also provides time to market and risk mitigation that you do not get because of the ability to customize your core. Oops. Now, get back to the why, right? We talked about earlier, we had instruction set, open standard. It enables us all to take a look at I like how you mentioned, John, where we can differentiate the way we solve problems, right? Modular ISA to match processor resources to the application. So that is the ability that you can get the basic extensions so that your software that you might want to procure on the open source will fit from one solution to another. But we do have the ability to actually customize, either add custom instructions or add extensions that will actually provide your application with additional benefits. So Risc-V Nonprofit Foundation maintains the stability, which is, I think John mentioned before, is a very key part of this, right? So that we understand that we have a stable foundation. For example, if you're using the M extension, once it gets frozen, you are comfortable that it will stay, right? And that if I'm in M extension compatible, then I can run M extension compatible software. Development of open source drivers, operating systems, and tools. That's part of the ecosystem. We have a growing ecosystem. Remember back in 1989, we were told we could not support our Solborn's computer or processor wouldn't be able to be sold because no one would create an ecosystem for a single vendor with a new architecture. But with all the different companies who are supporting Risc-V, the ecosystem is growing. So there's a growing amount of open source drivers, operating systems, and tools which enables you to implement your Risc-V. So I'm going to do a demo tomorrow at 2:30. So in the demo theater, it's through customization, architect your ambition. So I will actually be doing a demo on how you can actually customize your processor. And the demo will include several different ways of improving your ISA for a particular application, as well as improving your architecture for an application. So it's a way of architect your ambition to meet all these different type of processor needs that you need for the IoT and DSP markets. And here's my contact information. Please contact me if you have any questions. I'm based here in Seattle, but I actually have responsibility globally. So I do run the university program, and we are actually actively engaged in 3 pillars. One pillar is we actually sponsor PhD students in research for master thesis projects. We also support professors in their research and in their projects. We actually have a dedicated support team working with the universities, which I think is really unique, that we have a dedicated set of innovation engineers working with the universities. And lastly, we also create curriculum and make available for free for the universities if they would like to do some project-based learning regarding Risc-V. So that's my presentation for today. Hopefully you can make it to the demo tomorrow. But is there any other questions that you might have? Yeah, you know, in theory, the Risc-V architecture is meant to support all different implementations of it because it's an ISA standard, right? So,
But it's a digital standard.
yeah, yeah. So I apologize, I don't have enough experience to address that one, but I don't see.
AOU would be the main difference.
Yeah, yeah, that sounds good. I mean, actually, these are the type of problems that I like to actually do work on. So actually, a couple of people from Codicip know those are things that I like to work on. So yes, I'd like to talk more about that. Anything else? Any other questions? Thank you very much for everyone who was brave and actually answered my questions. So I appreciate the time to talk about Risc-V.
All right, thanks for coming. My name is Ted Spears. I work at Microchip Technology in the FPGA business unit. As I think it was pointed out earlier by Callista, we're a sponsor of the Risc-V Summit, and your Wi-Fi password, I think, is pound Microchip FPGA. I'm also on the board of directors of Risc-V International and have been so since its inception back when it was Risc-V Foundation in 2016. So, you know, first, you know, I'm really happy to participate in the Risc-V 101 session today. And my portion is going to be talking about the Risc-V ecosystem. Yeah, so there's the context and the whole section. So there's a lot of overlap actually, and messages will be the same. So we should come away today, hopefully understanding, have a feeling that the Risc-V ecosystem is ready, but also more importantly, where do I go when I want to find out or get something done with Risc-V? And that's mainly what I'm going to be doing, you know, teaching people how to fish, so to speak, in the Risc-V ecosystem. So some important context. So what you see here is there's a software ecosystem at the top, and then an implementation. That's the actual hardware that you get. It's a chip that someone makes. So you have software, and you want to run it on a piece of silicon. And the ISA, which is what Risc-V is the instruction set architecture, and it's really the contract or the interface between the hardware and software. It's an important distinction, and it really defines what Risc-V International is about. We're defining that ISA level so that people can make silicon, and the software that's out there can run on that silicon because of the instruction set architecture is defined. So, you know, there's a lot of ways to break up or slice this, but one of the ways is open closed, and this is an area that's actually a lot of confusion about Risc-V. You know, is it open source? Is it closed source? What is it? So, to kind of step through here, we'll see a lot of these type of slides. The history of compute. This is one version of the history of compute. We started out in the PC era, anyways. You know, there's one operating system. It was DOS or Windows. That was closed, the proprietary operating system, and you know, a whole bunch of software ecosystem, of course, around Windows. But Windows was kind of the centerpiece. And there was kind of one instruction set architecture. It was the x86, and there's actually two people who could build x86s. It was Intel, and they licensed AMD. So you had a proprietary ISA, proprietary software, and these guys also controlled who could make the hardware. So for the longest time, the first era of the PC, basically the whole ecosystem was closed. It was an excellent ecosystem for sure. One of the things that people had control, so they had complete control, and they were able to charge a lot of money in the beginning of an industry, and so they were able to build out this ecosystem. But eventually, people started focusing on open source. And the open source revolution, you could probably pin down the date. Certainly GCC, Richard Stallman, invented a compiler that anyone could use that would compile, C and Fortran and other things to the Intel x86 architecture that was out there. And then in, I think, 1993 is when Linux, there was an email sent out that said, here I have this operating system, check it out. And that was Linux. I believe that was 1993. So now the world started to cleave into kind of an open and closed world. And then around the same time, maybe before, in the late 80s, a new instruction set architecture based on something called Risc came out. And there's a lot of Risc architectures, but ARM here serving as a dominant one. So they came out with a new ISA to compete with x86 eventually. It started out at a lower point than x86, but is definitely a competitor. But what ARM really brought to the market was they didn't say, here, buy our chips. They said, buy our IP, and then lots of people could make chips with the ARM. So now other people could get into the business of making chips. You listed a few examples here. They obviously dominate the cell phone market. So Samsung makes ARM-based chips, Qualcomm, Marvell, Apple. So ARM really, by this idea of taking their IP and selling it to other people, allow other people to make products with the ARM ISA, was really changed, revolutionized the industry. But that was all still closed, basically. So Risc-V comes along. It's not the first open ISA, but it's going to be the most important one. And we said, we'll make an ISA, but anyone could change the ISA, edit it, customize it, use it for their own purposes. And so we had an open instruction set, and what that's really implemented or enabled is, instead of one provider for your Risc-V ISA IP, like in the case of ARM, there's going to be a whole ecosystem or universe of Risc-V IP suppliers, and they'll implement Risc-V. So the ISA is fixed; it's open, but the suppliers, any supplier, can make a Risc-V IP targeted for a new market, something that's coming up quickly, up to certain customers' needs. So this is how Risc-V kind of is changing the landscape of compute. So here I showed 4 examples. We had talks already today from Codesip and Sci5. NVIDIA I listed. They're not an IP company. But they use Risc-V and adopt it in their own chip. So the history of Risc-V, the early adopters are people who made their own, didn't tell anyone about it, and just embedded it in their chips. So if you buy an NVIDIA GPU today, that's on the 2nd or 3rd generation, there'll be tens to dozens of Risc-Vs inside that. But these, you kind of can't quite see the line there, but these are not open source IP. These are actually proprietary IPs. So this is kind of a distinction that the industry needs. The ISA is open. It can run both closed source software and open source software. But a lot of different people can implement proprietary versions of their IP, and then they're going to go sell it to you and license it. But that's not the end of the story. There is open source IP. So if you don't want to pay one of these vendors for the IP, excuse me, you can go out and actually go to get a open source version of the IP. So I listed here 2 examples. One's something called the Open Hardware Group. They have a whole bunch of open source RISC-V IPs. Early adopter of RISC-V is a company called Low Risk. Another example, but there's lots of, if you go to the web, you can find lots of examples of open source IPs. And these aren't just toys, they're actually implemented in designs that people can buy today. So now we get to the implementation SoC, in a sense this is no different than what ARM enabled. Lots of people implementing Risc-V today. So, NVIDIA, mentioned already, people who use ARM before are switching to Risc-V because they see the benefits. And then Microchip, my company, an early adopter of Risc-V. And, kind of the reasons were, we did want to innovate. We didn't like, you go to ARM, I always like say, if you go to an optometrist, they say, does this look better? This look better? ARM is like this, like you want this core or you want this core. Well, now with Risc-V, you can basically you can get whatever you want. You can make your own. You can go to one vendor and say, how about this? And well, we don't have that. You go to another vendor and they'll deliver that to you. So this is a key enabler of Risc-V. So a lot of proprietary implementations of Risc-V, and then there's actually a whole open source project built on Risc-V on the low risk Risc-V. It's called Open Titan. It's a root of trust program run by Google. So Google uses Open Titan for their root of trust and in their data centers, but anyone can go use this silicon implementation of root of trust. So it's a complete open source ecosystem. So that's kind of the context here. But, like I kind of, emphasized, where the magic happens, what's really different is we have the open ISA and then lots of implementations of the ISA that are out there. And then everything else kind of fills in around it. It's not differentiated. It's just a matter of, is it there? Is it there yet? And the answer is yes, and hopefully you'll understand that by the end of the talk. So points of entry. I'm a user. I want to learn about Risc-V. I want to build some hardware with Risc-V. I want to buy some Risc-V hardware. I want to participate in Risc-V. So where do I go learn how this? You could go look at my pitch, but better thing is just start at these obvious points of entry. And one is, Risc-V International has a website, risc5.org, and they have one kind of key point of entry. It's called the landscape, and so you go to this website on Risc-V, and there you see. Basically, this is, every company has a slide like this, an ecosystem slide that shows all the partners, the whole layer, the whole stack. And so here it shows, from application software to operating systems. And then what's different, it goes to all these different implementations. That's different, that bottom row. So you see all those different suppliers. So you can go to, I mentioned Andes, we talked about CodaSip, but you see Cordis, Imagination. There's literally dozens of people making implementations of Risc-V. So this, this slide is taken from that website, Risc-V landscape, and and of course each of these, if you go here and say here's where do I want to start here, there's a link. Each of these are hyperlinked to where you need to go to learn more. So that's a good resource if you want to, like I said, jump into the Risc-V pool, and as you can see, very, very robust and complete ecosystem of open source and closed source here. So you see Android, big announcements about Android. Android fully supports Risc-V. You see FreeBSD, it's one of the early Unix releases of software. That's open source Unix. We talked about I think Green Hills and Wind River, these are proprietary software. They all support Risc-V. So the Risc-V ecosystem is there, and this is kind of one entry point that you can go to. Then you can also go to risc5org.exchange, and this is a good spot here. Maybe need to blow this up, but you can, this is basically a whole directory of the Risc-V ecosystem, and you can sort or search for hardware, Risc-V cores, Risc-V software, Risc-V solution providers, and Risc-V, Learn Risc-V, Risc-V educators. So here we're clicking on Learn, and you see it's all, alphabetical. We have an Arabic course in computer architecture, Risc-V, tutorials on Risc-V MCU. So this whole thing is available. If you want to learn about Risc-V, you can go, and then of course there's the selections on the left-hand side to kind of further refine your where you want to go and learn about Risc-V. So just stop here or make a key point as far as learning. Risc-V, I like to say, is the lingua franca of computer research. So all universities are switching to Risc-V. The students, if you're going to be hiring students, you need them to understand hardware. They're going to be trained in Risc-V. So this is one thing that Risc-V enables. University doesn't want to just use a fixed implementation of the core. They want to be able to experiment with it, change with it. This is why Risc-V is really important in the education, which is then going to be the future of compute. It's all going to be, all the students are going to be Risc-V trained. So other points of entry are these Risc-V adjacent organizations. So I mentioned one, Open Hardware Group. So this is not Risc-V International, but it's a group that says, okay, Risc-V looks great, and let's help people build Risc-V chips using these open source IPs. So there's a number of companies are involved in, and mainstream companies are part of this group, which are basically, if you don't have your own silicon department, you can go to them, and they can help you start getting, with the tools you need and the contacts and so forth that build a full Risc-V based system on chip. There's another one, there's going to actually be a whole talk today about RISE. It's the Risc-V software ecosystem. It's a Linux project, and it's if you go back to that first slide, they're basically going to be stewarding and making sure that open source software ecosystem is completely robust and built up, and they're going to be making sure that dotting the I's and crossing the T's of the Risc-V open source software ecosystems. There's a whole talk today, a little bit later, about what RISE is doing for the Risc-V ecosystem. But again, they have a website if you want to go learn about where Risc-V open source software is going to happen. So then, the next thing is, well, go to vendor sites. So every one of those links I have, you go to those vendors, and that may be a good way to get started in learning about what's available in Risc-V. So, could then, show some examples, Green Hills software. So if you're in a certain industry, like automotive or defense, industrial safety, chances are your whole organization is going to be, the Green Hills is actually the center point of developing products for your industry. There's many examples like this, but Green Hills is one. So if you go to the Green Hills website, you click on products, and they have a core supported, and this is the Risc-V page. So their whole product line is going to be supported by Risc-V. So if you're in a company and you have some operating system or development environment that your company uses, you don't have to worry. Chances are you don't have to worry about, is Risc-V supported? It's going to be fully supported. So another point of entry, the core providers. I said the core providers. This is really what differentiates Risc-V. There's going to be lots of different core providers. Sci-5 is one, Codicip, but I just showed some examples. Andes, early adopter of Risc-V, so they built out a their ecosystem on so the vendors have their own ecosystem. So you go there and start to learn about how that vendor's is your actual point of entry into the ecosystem. So you see Green Hills, IAR, Empiris, these are all part of the Andes ecosystem. And so then Andes is saying, I want to sell Risc-V, but I want to sell it to different marketplaces. So these companies, these software companies, or these IP companies, are building out one-stop shops for everything you need to develop a Risc-V product for different vertical markets. So here I'm just showing the automotive example from Andes. And then at the kind of the bottom, last but not least, it's the actual silicon providers. And so now we're going to switch to a commercial for microchips. So I got this T-shirt here, My5. That's our ecosystem. So to support our Risc-V based silicon. And so if you go there, you'll hit there, you hit the My5 ecosystem, and like Andes, we have CPUs, design tools, operating systems, solutions. And one thing about these ecosystem is actually alive. So things can happen really quickly. If you go to one of these suppliers and say, I need this, and if it's not there, actually it doesn't take that long for the ecosystem to move and kind of attack a certain problem. So the ecosystem is very dynamic. So if you're sitting out here and you go through and say, well, I didn't see this, it's not that hard to actually make that magically appear. And we'll kind of touch on an example a little bit later. So, our ecosystem is built on a chip we make called PolarFire SoC. So it's got a 5-core Risc-V application processor in it, embedded with an FPGA. So this is not a soft core that you program into an FPGA. It's actually a Risc-V application processor, 4-core running Linux, and then a 5th core to handle security and system management. Plus FPGA gates you need to attach or accelerators to your Risc-V. So now things start to get fractal. So we have a board. We have a chip, actually, but now we're creating our own ecosystem. So there's lots of places you can go to buy Risc-V silicon using our silicon. And so, this is our partner. So you can go to a company called Aries Embedded or Trends, people making SOMs, so that help you get to market in small form factors quickly with Risc-V. So, depending on your application domain, these customers or these partners, support have expertise in different domains. But so it's not just, you don't have to just go to Microchip to get hardware. You can go to any of these suppliers. And I'll just focus on one. There's a Beagle 5. So now it starts to get fractal. So we have some hardware, lots of people making hardware, but Beagle's expertise is to build ecosystems. So now you have an ecosystem that's created an ecosystem. And so Beagle just did their announcement. They're actually displaying, I already have it in here, somewhere in here. This is the Beagle Fire board. It's built with, if people are familiar with Beagle board, they used to build, ARM-based chips. They still do build ARM-based boards. Started with TI, but now they're branching out into Risc-V, and we're really proud that they've chosen PolarFire is going to be. They're not going to just be a microchip Risc-V outlet. They're going to be a Risc-V outlet for any silicon that comes out. You can imagine open source hardware, so you can get the schematics. You can build whatever they tell you how to build this board if you want to build this board, but then. They have whole software ecosystem supported, and if you're involved or plugged into something like BeagleBoard, you have this whole ecosystem kind of served on an open platter for you to get involved with the Risc-V. So we're really happy with this. The BeagleBoard announcement was recently, and they're going to be presenting here. So, back to the slide, where the magic happens. This having all these vendors lets Risc-V. It's going to let Risc-V attack any domain real quickly and rapidly. So there's like legacy domains. So telecom, IoT, AI/ML. That's kind of a new domain. So if you're a startup company, the quote I had is, I asked a VP of a startup, did the VC have a problem with you choosing Risc-V over ARM? And he said it would have been the other way around. If you went with them with ARM, they would have said, why not Risc-V? So anyone building new, entering new markets, it's the obvious answer to go use Risc-V. So AI/ML obviously rapidly growing. Automotive, important area in the future. Data center and cloud. So Risc-V is not all about small embedded processors. It's about data center and cloud and high performance computing. This all happened very quickly, like I said, for the legacy, but the future, that's where the future is going to be with Risc-V, because you've got all that engine for innovation, I think, because anyone could build their own Risc-V devices. So, just kind of closing, can this ecosystem be, this slide is something kind of illustrates the point. Can the ecosystem be used in anger? So this is a company called SkyCorp. We talked about legacy markets. There's going to be a huge economy on the moon, ultimately. People are all figuring out how to plan and put stuff on the moon. So SkyCorp said, we're building something completely new. We want to use Risc-V. They kind of did the same thing. Who makes Risc-V chips? A microchip. So they called us, and they got excited at what we had with Polar Fire SoC. And they said, well, we want to build data centers on the moon. So for data centers, we're going to need an operating system. So what's the number one operating system for Linux? Ubuntu. So they actually, made the phone call to Ubuntu, and Ubuntu came and said, oh yeah, we can support that. So I told you that the ecosystem is dynamic. This illustrates that the ecosystem is dynamic. So, this is actually fielded, a full-blown product, not developed by Microchip, using Microchip silicon, using Ubuntu Linux, is up on the space station today as a test platform for new hardware that's going to ultimately take Risc-V to the moon. And if you've followed the news on Microchip, and it's going to take Risc-V to Saturn, Jupiter, planets, exoplanets, and Risc-V is definitely going to own that market. So, kind of concluding, hopefully, Risc-V is ready. So you saw the kind of the breadth, the charts showing all the different components are there. It's accessible. So, kind of a lot of the talk was showing you how to, get what you need to help the ecosystem work for you. And then finally, it is enabling innovation. So that's my talk. Thank you.
I hope everybody got some caffeine out there, so they're awake. I got my caffeine. If I'm talking a little bit too fast, just raise your hand, tell me to slow down. But we're going to change direction a bit after the break here. Those first three talks that we had were really focused a bit more about why Risc-V, and an introduction and history and ecosystem and just questions like that. So we're moving off of the sort of abstract why Risc-V, and we're going to assume here that you've made the decision to go with Risc-V. And so what are you going to do now? And the first thing that you're going to do is figure out what you're going to do about a Risc-V processor. And this is a more or less classic make versus buy decision. So that's what we're going to spend the next few minutes talking about. So I'm from Empiris. Empiris does not build Risc-V processors. We're actually a tool company. We build models, we build simulators, we build other IP. So why am I up here talking about processors and make versus buy? Well, I'm up here because we see nearly every Risc-V project and processor. It doesn't matter whether it's a make or a buy decision. We're going to see pretty much everything. We don't care what your decision is. We don't care at all. We have relationships with nearly every major Risc-V processor vendor. We participate in the open source projects. We have customers that are building their own. So we don't really care. What we do care about is that when you make the decision, you do it with appropriate thought and care going into that decision. So I will give you just a quick pitch here. What do? We start with models. We've got models of the full Risc-V spec, including the stable unratified versions, and you can add custom instructions to that. That becomes a reference model. That reference model can be used for verification, something really important in the Risc-V world. Can also be used in a virtual platform or software simulation environment for software development. So that's Empirus. We're models, we're tools. And actually, as we've talked about adoption and where Risc-V is going, one of the interesting things in this last month leading up to the Risc-V Summit is that in the tools area, we've seen Synopsys, one of the major EDA players, not only join the Risc-V International Organization, but join at a premier level. And so Synopsys is actually investing in Risc-V here and sees the opportunity as a tool provider to support the Risc-V community. So I said we see most projects. So we've got a nice customer list there. We've got a list of processor IP partners. We've got tool partners. In the bottom left, there's this thing called Risc-V OVP Sim Plus. It's a free instruction set simulator that we provide, and there are more than 100 organizations using the free tools, plus our commercial partners. So there's something like over 150 different Risc-V projects that we've seen. So on to Risc-V, enough of the commercial. So Risc-V is an open standard instruction set architecture. We heard that this morning. The freedom enables domain-specific processors. That's a key piece of this, and it's the freedom and not the free that is driving and accelerating the Risc-V adoption. So what are the sources of implementations, of the Risc-V processor implementations? Well, we've talked about processor IP vendors, Sci-Fi, Andes, Codesip, and down the list there. There are also open source implementations. Ted mentioned a few of those, like Low Risk and Open Hardware Group. And then you can build it from scratch. And there are organizations that are absolutely going and doing that. But the thing that we see, because of the freedom in Risc-V, is that with all these implementations, custom instructions and configurations are going to be used. And then with all these implementations, even with well-verified processor IP, the processor plus the custom features must be designed and verified. And then don't forget about the software cost for the tool chain, for software porting, for the other software side of it. So there are a whole bunch of factors that need to come into this decision about which processor or how you implement the processor. So in no priority order, we can look at IP ownership. Do you own the IP or are you licensing the IP? If you're licensing it, what is the licensing cost? And then the PPA, what is the power performance area for the core? So that's one category or one set of factors. And these are actually relatively easy to estimate, these costs and benefits. But now there's some other things. If you're going with open source, if you're going to build your own, what are the resource requirements for the base processor? What's the cost of adding custom instructions? What's the cost for the design, for the verification, for the tool chain, for the software porting? And there are other costs, other factors that go into this as well. With these costs, though, this is much more difficult to estimate. So this is where the care comes in. This is where you have to think through these things and figure out and do these trade-offs between the custom instructions that you're adding and the resource and the other costs that it's going to take to implement those. So sources of processor implementations, there's a partial list of the processor IP vendors. There's open source implementations. There's build from scratch, and I've listed a few companies that are public about what they're doing with Risc-V. Ted showed that landscape chart, and it's up on the Risc-V website, so feel free to start there. There's also the Risc-V exchange that Ted showed in his talk. So there are a number of resources that you have to go and look and see who's doing what. So taking a look first at processor IP vendors and the pros and cons of choosing one of the processor IP vendors. So there are lots of choices. I listed, I think, maybe a dozen in that previous slide, but I think if I count them up, there are probably closer to 36 different processor IP vendors in the Risc-V community. That actually is quite a few choices there. And there are lots of choices for different feature sets, for the PPA trade-offs. There are even different business models between the different processor IP vendors. So that gives you lots of choices, and given the number of vendors out there, gives you a bit of leverage when you're choosing your processor IP. That's a good thing. So on the con side with processor IP vendors, yep, you're paying for a license. Okay, that's fine, but you're getting processor IP, so there should be value for the license cost that you're paying. And then depending upon who you're working with, it may or may not be easy to add custom instructions. And again, adding the custom instructions, custom CSRs, it isn't just adding them in, it's supporting those and what you're going to have to do with those. So you need to think about all that. But having said that, there are a lot of processor IP companies licensing a lot of Risc-V processor IP to a lot of SoC developers. So this is certainly an easy way to go. I think John, in the first talk this morning, said that Sci-5 had something like 350 design wins. That's a lot of processor IP to a lot of SoC developers. So certainly the processor IP vendors are a viable alternative. And just as one example here, we've got MIPS. MIPS had their traditional MIPS architecture. A couple of years ago, they switched over from that MIPS architecture to the Risc-V architecture. Mobileye has actually long been a MIPS customer, and probably their major customer. And Mobileye went right along with this switch. Actually, I have to believe here that these discussions, that MIPS didn't make this decision in a vacuum, that Mobileye knew exactly where MIPS was going when they made this decision. And so Mobileye, who probably has close to 50% of the ADAS market, something like that. They're a significant player here, and they're going with Risc-V for their next generation IQ SoCs. So this is a pretty significant endorsement of Risc-V by one of the major semiconductor players, and this is actually in automotive. That's pretty significant. So that's processor IP vendor side. Let's go and look at open source implementations now. So on the pro side, there are, again, quite a few choices. I listed a handful up there. I think Ted had maybe a few more. But there are also some companies or consortiums that have collaborated and put the effort into it. It isn't just sort of open source where some grad student has said, oh, I designed a processor, I'm going to put it on GitHub, call it open source, somebody can go and download it. These are actually serious open source projects. Low Risk is one, Open Hardware is another. There are a few others that are out there. And actually, I think T-Head is another significant one. So on the con side, depending upon what this is, sometimes there's a lack of support, including user documentation. So it's unclear with some of these open source projects how well it's actually been productized, if you will. It's also not always clear how much verification has been done. With the Open Hardware Group course, actually, that is pretty clear. Again, because of that lack of documentation, if there is such a lack, it may not be as easy to add the custom instructions, CSRs, et cetera. And then there are the resource costs with open source. You know, just not knowing exactly what you're getting there in some cases. What do you need to plan for in resources? So as an example here, I'll use Dolphin Design, a company that probably none of you have ever heard of before. They're a small company based in France. They build system IP. They provide design services. One of the pieces of IP that they build is a DSP subsystem. So they're starting with Open Hardware Group cores. Open Hardware Group is a consortium with a mission to build industrial quality open source Risc-V IP. The CV32E40P V1 has gone through comprehensive verification and has been implemented in multiple SoCs. That project was initially led by Silicon Labs. Actually, still currently, Silicon Labs is working on variations of that processor. But Dolphin needed more for their Panther DSP subsystem IP than in the V1. And so they've iterated that, and they're on this V2 project. It has DSP-like capabilities. It's higher performance. It's lower power consumption. It's a smaller code size for the software running on it. And then in addition to the public open source improvements to the E40P V2, Dolphin is adding custom instructions. So they're doing this thing where they're working in the consortium to add things that they think are helpful to everyone in the consortium and even in the community, but then they're adding their own proprietary custom instructions onto this. So yeah, they're making an investment in design, in verification, in the tool chain, in the software porting, but they thought that this was the best approach for them to start from a good base and then add their custom instructions in. They thought that this was the best trade-off for them in terms of features and resources and what they were going to get out of it. So that's another one of the ways that we can go on this. And then build from scratch is the third way, the do-it-yourself processor. So you can do almost anything you want functionally. That's a pretty cool thing. That's Risc-V. It's all the different extensions that we have with Risc-V. It's all the different subsets of those extensions. You can do almost anything. If you have the expertise, you can build a more optimized microarchitecture. So that's a pretty cool thing, because if you look at Andes or Sci-Fi or Codicip, or you may be able to do something better from a performance or power consumption perspective. If you already have a proprietary ISA, switching to Risc-V reduces the business risk. Our first customer at Imperis, our first Risc-V customer, so we existed well before Risc-V. We support many other architectures besides Risc-V. But our first Risc-V customer had a proprietary architecture. And when we asked them why they were switching to Risc-V, they said, well, it's going to be just as easy or just as difficult to build the processor. But actually, we only have one guy in our company that works on the compiler for our proprietary core. And if that guy gets hit by a bus crossing the street, we are in deep trouble. But now, because they're part of the Risc-V community, they've got a whole ecosystem that's supporting them. And that's what's happening with teams with proprietary architecture. You can look at what NVIDIA did as well. You can look at, I think Seagate is another one. There are a few others that have switched from proprietary architecture to Risc-V. They had the processor expertise in-house. They just wanted to reduce their business risk. So there's no license cost here. There are no concerns about open source quality. But on the con side, you're paying for it in resources. You have to do everything. And it hasn't been tested. So if you're getting an open source core, if you're getting a core from from one of the processor IP vendors, they will have been testing it. Likely there are going to be other users of that core, and so it's going to have some additional testing there. But if you're building it yourself, you're building it yourself, and you have to trust your team on that. And I mentioned Seagate before. Seagate, this is actually an announcement from the summit 3 years ago. Seagate actually produced two different Risc-V cores, one optimized for area, one optimized for performance. They also had different functionality in the cores. One was more for moving data in their hard drives. One was more focused on the security aspects of it. So they were able to do exactly the things that they wanted to do with Risc-V. Had been doing, for the most part, with proprietary cores, but now it was better to move to Risc-V. So, estimating costs. So this trade-off thing of if you're going to build it yourself, if you're going to add custom instructions, how do you go and estimate those costs? Well, let me talk about processor verification as an example. I've mentioned you've got design costs, you've got verification costs, you've got the tool chain costs, you've got software porting costs. So processor verification, it shares some techniques with general SoC design verification. And that's good. So all the UVM stuff that people have been doing, all that experience helps. But processor verification is more difficult because of the large state space of the processor. It becomes a lot more complicated to do this. You need a good reference model to be able to work with this. So there are differences here versus what you're doing with the rest of the SoC. Processor IP companies, if we look at those historically, if we look at ARM or if we look at MIPS, these processor IP companies consider their verification flows and environments more valuable than the RTL itself. That never gets out of house. So these companies consider verification hard work and very important. That's an easy way of looking at it. Having the reference model, as I said, is a necessary but not sufficient condition for processor verification. You also need a solid methodology. You need verification IP. You need other technology. You need things like functional coverage. I mean, it's verification. There's a lot that goes into it. And some of the simple things that you think of, like doing signature compare or a post-simulation trace compare, is not sufficient for the complexities of a Risc-V core that you're going to be building that's going to support interrupts, that's going to support privilege modes, and on like that. And then just one reference to a paper coming, I think tomorrow, booting Linux or running other software is similarly incomplete from a verification perspective. One of our university partners, Harvey Mudd College, is going to be talking exactly about this sometime tomorrow afternoon. So how to estimate the processor verification costs? It's not easy. There's no simple formula or spreadsheet, but you're going to need to take a swag, a scientific wild guess at this, and you need to figure in all these things. And then you need to go and do the same thing on the design side, the same thing for the tool chain, and the same thing for other software porting. So just to sum up here, the Risc-V freedom, again, it's the key thing. The freedom enables domain-specific processors and motivates the increasingly obvious choice of Risc-V. How to choose a processor, the standard metrics, the IP ownership, the licensing cost, and the PPA. But with all the Risc-V implementations, the custom instructions, custom configurations are going to be used. And with these, you're going to need designing, verifying, toolchain development, software porting. And again, when making this processor decision, be careful to factor in the added complexity of the custom instructions and what you're going to need to do. So that's me. You can find me on LinkedIn. There isn't another Larry Lapidus there, so I'm pretty easy to find. And for the next few days, I'm going to be around. We've got a booth in the exhibits, and tonight I hope you'll join Imperis after the general member meeting at 5 p.m. Party downstairs, bottom of the escalator, hang a right. Thank you.
Everybody enjoying Risc-V 101 so far? Seems like it's been a very, there's a lot of information compressed into a very small space. But that's why we're here. So good to see everybody. My name is Jeffro. I work at Red Hat. I worked at Risc-V International for a number of years. And it's great to be here. I'm here to talk about the software ecosystem boiled down into a very small nutshell. The software ecosystem could easily take up an entire day. It's very complex, as it is with any architecture. But the first thing I want to talk about is upstream. There are three things. Here we go. Sorry. Real question is, where is software being developed in the Risc-V ecosystem? What I wanted to cover today was, in general, upstream projects, software development and tracking of that development within Risc-V International, and then the RISE project, which is a new project within the Linux Foundation that has just formed this year. So diving into upstream, you'll notice on these slides that a lot of this is stuff that is already out on the Risc-V website or on the Risc-V wiki. These are great sources of information to be tracking whenever you are looking for software or looking to see if something has been done or needs to be done. In particular, at the bottom of this page, which is the homepage for the wiki, you can see there is a button there that says Risc-V Software Ecosystem. So you want to start there, and that boils you down into this page, which talks a lot about the ongoing porting work and development work, that is going on within the ecosystem, particularly within tool chains, operating systems, emulators, simulators, language runtimes. There's a ton of work going on here. One thing I also wanted to point out is that there is another page about how to contribute to this Risc-V software ecosystem, and that is, partly from a developer point of view and partly from a business point of view, if you wanted to talk to the folks at Risc-V. There is a software ecosystem developer, Isaac Shute. I'm sure that he's around. I haven't seen him yet this morning, but I'm sure that he's going to be around this week. There are also many upstream open source communities, and one of the things I'm talking about here is specifically about open source. I'm not talking about the wide amount of proprietary software that is also being developed in the Risc-V ecosystem. But upstream, there are quite a lot of projects that are addressing open source. Certainly Linux, Android have been talked about. On the toolchain side, GCC, LLVM, Clang support now. And with operating systems, Yocto project supports Risc-V. Certainly the major Linux distributions, Ubuntu, Debian, Fedora, which is my personal favorite, Zephyr, which is one of my second favorites, and then FreeRTOS as well, and I'm sure that there are many that I'm forgetting here. If you have a specific need, I would highly recommend going to that community's website and asking questions. I'm sure that they are covered there. So I wanted to talk a little bit about the Risc-V technical working groups. This is the page on risc5.org that talks about the technical forums, and one of those is probably I think it's the second longest standing mailing list in the Risc-V ecosystem, and that's the software dev mailing list. It is still quite active. It is a Google mailing list, so it's very easy to join. Strongly recommend going and taking a look. There are also the technical working groups within Risc-V International. This one I just picked out was the applications and tools overarching group within the technical working groups. And what you'll see on this page is that there are a lot of software-specific SIGs. QEMU is covering emulators. There's the JIT and VM SIG for just-in-time just-in-time compiling and virtual machines. Audio and video codecs, crypto libraries, DSP libraries. There's simply quite a lot going on there. And you'll notice that most of them are SIGs, which are special interest groups. It means they don't have specific deliverables. They are simply there for people to have open discussions about these topics. We also cover automotive, like in the automotive SIG, which is more of an ecosystem-oriented SIG. We cover software there as well. I'm sure they also cover it in functional safety and high-performance computing. You know, there are so many technical working groups within Risc-V. I think it really pays to just look around and to talk to folks at this conference if there's a specific topic that you're interested in, software-wise. And don't forget GitHub. There is a very robust set of software repositories on GitHub. You can see down here there's an entire Risc-V software area. There's also Risc-V Android software upstreaming. These are software that's been developed within this community. So it's very important. And indeed, there's also some development software such as Spike, a Risc-V simulator that's available that was developed within the Risc-V ecosystem. So, the final thing I wanted to cover in my brief talk here is the RISE project. RISE was formed by 13 organizations back in May of this year, specifically to provide resources to this very large software ecosystem. A lot of work has been done by the community, very much by individuals working in various communities on software to support Risc-V. RISE wanted to kind of formalize that and bring a bit more resources to it. So it is formed as sort of a consortium to provide personnel. So each of the founding organizations does have one person specifically, at least, working on Risc-V only. And there is also a pool of money, and there is now an RFP process within RISE for people to submit projects to be covered. And so there are actually 3 of those in flight right now, and which we do cover in the social media and on the RISE mailing lists. So here's a kind of an overview. I actually stole this from the TSC talk that will be happening on Wednesday. There will be a RISE TSC presentation on Wednesday to talk all about the different technical projects that are going on. So just consider this to be a sort of a teaser for that. Really, the goal of the project is to raise the quality of platform implementations to match other architectures. And I think that the TSC is very active and in supporting this goal. Work does not necessarily happen directly within RISE. The entire idea of RISE is to provide resources to work in these upstream projects. So that's where the work is happening. So it isn't something that you would want to go out and you feel like you need to go out and join. I mean, if you wanted your company to join Rise, would be more than welcome. But it's also possible to work with the Rise folks directly in these upstream projects. So there's another picture about Rise, exactly what it's up to, and our relationship with Risc-V International. That is one of the things that's very important, is that this was formed as a separate project within the Linux Foundation. But Rise is very much in contact with the technical side of Risc-V International and the marketing side as well. We want to do some collaborative promotion as well. So this is an overview of the TSC working groups. You can see that there are a number of different areas covered. Everything from simulators and emulators to firmware, compilers, and tool chains. My colleague Redbeard works on the Linux distro integration list, where there's a lot of discussions going on there about platforms that are appropriate for various distros, specifically in data center, but also for other distro purposes, including automotive. And it's also important to note that all of the members of Rise are also Risc-V International members. That's actually a requirement to join Rise. So these people also, you will find them in the Risc-V International working groups as well. So there is Rise has sponsored a lounge I think it's downstairs. Is it downstairs? Thank you. So if you'd want to continue the conversation about software, somebody from Rise will be in the lounge the entire time during the event. We'd be happy to sit and have a discussion. And so that's the plug for Rise. And that was all I really wanted to cover. I don't know if I've been talking really fast or if my 15 minutes are up, but it's all good. So any questions about software? I've answered everything. That's fantastic. That's never happened before. So, okay. Well, thank you very much.
My name is Martin Maas. I'm from Google. And I'm going to talk about how to get involved in Risc-V technical groups. So a few words about me. I'm a staff research scientist at Google DeepMind. I've been involved in the Risc-V project since the early days when I was a grad student at UC Berkeley. And at Google, I help coordinate our involvement in the various different Risc-V standard committees within Risc-V International. I'm also the chair of the J extension group, which is working on hardware support for managed runtime. So we work on things like a pointer masking standard, instruction data synchronization, and in collaboration with the runtime integrity group, starting to look at memory tagging. And I want to emphasize that in this talk, I'll be speaking in my capacity as Risc-V group chair, not for Google. Okay, so why get involved in Risc-V standards? There are lots of different reasons. And I think the high-level bit is really that Risc-V standards are evolving at a rapid pace. And this is an opportunity in being involved in shaping the ISA from a lot of different perspectives. So if you work in hardware, for example, being involved in Risc-V standards means that you can be a part of making sure that those standards match your microarchitecture and fit your different requirements. If you work on software, you can help ensure that Risc-V standards meet the requirements of your software and are maximally useful for the different use cases that the software ecosystem encounters. If you work on platforms, you can make sure that Risc-V fits into your existing ecosystems and matches best practices and fits into the various different application scenarios where Risc-V might apply. And if you're a researcher or a domain expert, this is an opportunity to actually apply research in a real-world setting and translate it into practical industry impact by getting research results into an ISA. So lots and lots of opportunities to be involved from lots of different perspectives. But the question that might arise is how do I get started? It all seems very intimidating. It's a very large organization with lots of different work streams going on. So how do I get started? And so this is what my talk is about today. And I want to talk about it from three perspectives. So I'm going to start by talking about the Risc-V organizational structure to give a different overview of what the technical side of Risc-V International actually looks like and what the different groups are where one can get involved. I'll then go through the life cycle of a Risc-V standard and show you how do we go from an idea for a standard all the way to a ratified standard in the Risc-V ISA. And then finally, I'll talk about how to get involved in these different processes and where to best get started. Okay, so what does Risc-V International look like? And I want to emphasize that I'm focusing on the technical side here. There's a lot more on other parts of the organization, but this is basically the structure where the technical work happens. And so at a high level, there is the board of directors, that the technical steering committee that is kind of voting on kind of standards that gets them across the line to ratification, for example, and makes a lot of the higher level technical decisions. There's also a tech chairs meeting, which brings together the chairs from the various different groups and looks at things like ratification plans. And then there are a number of horizontal committees that oversee a particular area within Risc-V International. So for example, there is as Jeff already mentioned, there is an applications and tool HC, which is looking at that part of the software ecosystem. There's a security horizontal committee that is looking at security related topics, etc. And within each of these committees, there are groups that pursue different work streams within that area. And some of these groups are overseeing a broader type of work, and others are working specifically towards standards. If the standards are ISA standards, these groups are called task groups, and they not only report to one of these horizontal committees, they also report to one of two ISA committees. There's one for privileged ISA and one for unprivileged ISA. And basically, this ensures that you both have represented the higher, the kind of higher level goal of that standard, like for example with security, and also have a coordinated way of ratifying these different ISA extensions. For ISA extension, there's also an architecture review committee, which basically reviews the various different standards and ensures that they all fit into the broader picture of the ISA. There's two special groups, profiles and platform, which exist outside of the structure, and that we'll talk about in a bit as well. Okay, so those were a lot of different groups. So what does it actually mean? And basically, we saw the ISA committees. Those are basically overseeing extensions that go into the Risc-V instruction set. So anything that ratifies an instruction set extension in some way is going through one of these ISA committees. Then there are these horizontal committees, which are overseeing a particular topic area, and so groups oftentimes report either to a horizontal committee or to a horizontal committee and an ISA committee. There are different types of groups. There is the special interest groups, which oversee a particular area or work stream. So for example, one family of standards or one area within software or infrastructure, and there are long-standing groups that basically pursue this area and might over time pursue a number of different standards. And then there are task groups, which are more focused, and these are technical time-limited groups whose role is to finish one standard, get it into ratification, and then disband. And so structurally, the 6 report to horizontal committees. They oftentimes spin off these task groups to actually get ratify the standards, and then they can report into different overarching committees as well. So what do these standards groups do? Essentially, there are 2 different types of standards. There are ISA standards, which basically add extensions to the instruction set. So things like vector, floating point, etc. Those would be ISA standards because they modify the ISA. And then there are non-ISA standards, which still are standard like a security model, but do not actually modify the instruction set itself. They both get worked on by similar types of groups, but they have slightly different requirements for when they get ratified. There are groups that pursue other areas as well. So for example, there are groups that oversee a particular part of the software ecosystem, like some of the groups that Jeffro talked about, or there are also groups that produce gap analyses for different sectors that can then feed into informing how a particular area should proceed over time. And I want to give a couple of examples of the different kind of groups to give you a bit of a flavor of the kind of work that is happening. As I mentioned earlier, the platforms and profiles groups, they exist a little bit outside of the structure, and their role is to define high-level standards that provide compatibility within Risc-V. So profiles define standardized versions of the ISA for binary compatibility. So for example, they define a particular set of extensions and a particular set of settings that then can be targeted by binaries, Linux distributions, etc. And I think this was what was earlier referred to in as RVA22, RVA23, etc. So some of the earlier talks mentioned this already. And then the second group of this kind is around platform standards, which define a standardized environment outside the immediate CPU and instruction set, but once again to have a common target for Risc-V to basically run within. Next, there are the two ISA committees that I mentioned. And to give you an idea of the kind of things that these committees might oversee, the privileged ISA committees, for example, looked at things like cache management instructions, runtime integrity, control of transfer records, which is basically a performance profiling ISA extension. And then the unprivileged committee, you have things like floating point, you have a vector sig, you have a dynamic language, which is a group that I oversee. And so these are things that directly modify the ISA. Then within the software horizontal committees, you have different groups that oversee particular types of applications. So for example, there is an AI/ML group, there is a group for managed runtimes. On the privileged side, there is a group for hypervisors and trusted execution environments and so on. So these groups oversee something more on the software side. And then there are a number of other committees. There is the Security HC, which oversees standards related to security. There is ISA infrastructure, which is things like simulators and testings. There is SOC infrastructure, which contains things like debug standards, QoS standards, etc. And a technology horizontal committee as well, which looks at different sectors and how Risc-V intersects with these different areas. And so, as you can tell, there is a very large number of different groups, but they all oversee very specific areas. And so looking at these different groups is a way to figure out what is the area that you're most interested in. Okay, so now that we've looked at the overall structure, I now want to go into detail of what the groups are actually doing and how a Risc-V standard goes from an idea to something that is actually ratified and becomes part of the Risc-V ISA. And in order for a idea to become a standard, there's actually a number of different things that need to be provided by the groups working on it. And this is a very, very simplified list. There's a more comprehensive version of this, but I think it gives the high-level idea. So the key portion of an ISA standard is a standard specification, which is a document that is describing the standard, and there is a particular way that it is written. It's following certain standards, best practices, and so on. Then there needs to be a proof of concept, which is an implementation that has all the necessary components to show that the standard is actually viable and works in a real environment. There needs to be a formal model. Risc-V uses a modeling language called Sail, and basically, as part of ratifying a standard, that standard gets added to that model. Similarly, there is infrastructure for test suites that a newly ratified standard also needs to provide. Then there is a whole area of ecosystem support that's very dependent on the extension and what type of functionality it's adding, but it includes things like software support, simulator support, support in the software ecosystem that is being targeted by that standard. Now, the standard progresses and is building out more and more of these different deliverables. And once it has reached basically a stable point, it's been approved by the architecture review committee, etc. Then it goes into public review, where for 30 days it will be posted and everyone can provide feedback. And then that feedback gets incorporated. And then finally, once all of this is finished, there needs to be sign-off by various different committees, TSC and board. So there is basically a whole lot of things that need to be provided, but there is also a process by which a standard goes through these different stages and starts from an idea and then creates more and more and more of those over time. Okay, so how does a new standard start? And a new standard typically starts by kicking off a new group that will be working on the standard. And so the way that a new group is created is by working with a sponsoring ISA committee or a horizontal committee to draft a charter that basically sketches out, this is what will go into the standard, this is the purpose of the standard, these are the use case, etc. And this is usually driven by an acting chair and vice chair who basically write this initial charter, they build interest, they bring others who are interested in this area, into this group and are basically sketching out this is what the group will provide. Once this preliminary charter has been drafted and there's sponsorship from the owning IC or HC, then it can go into kickoff, where it provides a call for a chair or vice chair and vice chair of that group, and basically makes this group formal. Then once all of this is finalized, it gets signed off, and then the group is active and can start to perform its group-specific work. In the case of a TG, that usually means that it produces the deliverables for the standard that it is ratifying and then disbands, whereas SIGs exist in a longer term until they are explicitly disbanded. So they can exist for a very long time. Groups have different ways of doing this. Some groups have a lot of online meetings. Others are operating mostly via mailing lists. This is typically up to the chairs and the dynamics of the group to decide how they run it. For groups that exist for longer, there is an annual re-election of chairs and vice chairs as well. So within that group, the group then proceeds to actually work towards ratification of a standard. And to do that, they start with a ratification plan. So the group sketches out a plan with a specific timeline of how the different deliverables will be met and who will be working on it. And this is then presented and signed off in the chair's meeting. Once it is signed off, the actual work starts within the group, which means the group works on the specification, works on the different artifacts and deliverables. At some point, it will go to architecture review, and the group will iterate with architecture review to make sure that it meets all the requirements. And then at some point, all the necessary pieces are in place, and the standard gets frozen and enters this public review period. At that point, there are no more additions to the extension, and the only changes at that point are usually to address reviewer comments. And then once this period has completed, all the changes are incorporated, then the standards get signed off and becomes a full ISA standard and part of the Risc-V ISA. There is a fast-track version of this where this doesn't happen in a new group, but it happens within an existing committee. But otherwise, this process is very similar. Okay, so this is the theory, but how does it actually work in practice? And I think it depends very much on the specific standards. So some standards are very simple and are ratified very quickly, are maybe developed by a small number of people, and other standards can involve multiple dozen people working on them for multiple years. It depends very, very much on how large and complex the standard is. But one thing that all of the standards have in common, that it's very important to have a combination of experts in the room, both from software and from hardware. Because software will be using the extension and hardware will need to implement the extension. So it's important to have both sides represented there. It's also important to have a range of different perspectives. So for example, you'll want different types of software that might use the same feature. And you want to make sure that different types of microarchitectures or hardware implementations are represented. And finally, it's important to have subject experts who can speak to the particular area that the group is working on. So for example, experts on different machine learning techniques, if it's an ML-related standard. And it's also important to have representative of particularly important stakeholder projects for that standard. So for example, if a standard needs to be supported by one particular software ecosystem, it's important to have that software ecosystem represented as well. So how to actually get involved in these different kind of areas? And I would say the best way to get started in Risc-V International is to join an existing group in your area of interest and participate. There is a great way to figure out what the various different groups and meetings are. Risc-V.org has a calendar and has a spreadsheet with all the different groups. And so it's very easy to go and see these are all the different groups that are currently active and join meetings of groups that are of interest. Once again, some groups are doing their work in meetings, some mostly do it on mailing lists. And the best way to find out is to join the mailing list directly online, and then meetings will be announced there, or maybe the group will mostly do their work on the mailing list. This is a great way to meet new Risc-V members and become part of the community. And in particular, all these groups have always some work to do, be it on contributing to the spec, or to the testing, or the formal model. And so one great way to get involved is to volunteer for some of this work and basically become part of the community and contribute to Risc-V. And then by doing that, building up expertise and knowledge of the Risc-V ecosystem and Risc-V standards. And eventually this can build to something bigger, for example, eventually running for a committee position oneself. And one thing that is very nice about Risc-V is it's really a very open and welcoming community. It's really possible to just join any meeting and become part of a group, and there is not a like a process of formally signing up. The only thing that is necessary is to be a member of Risc-V International. Only Risc-V International members can join the meetings, but there are various different membership tiers. All right. So in summary, Risc-V is really developing at a rapid pace right now, and participating in the standard body is an opportunity to be involved in shaping the standard and working on something that gets used in real systems and is having the various different impacts that we've heard about throughout the day. But the impact is, whether areas in hardware, software, research, there's always something to do in these different groups across many, many different types of work. And the meeting are, as I said, they're open. It's very easy to join, very easy to become part of a group, and it's a lot of fun. So I would invite everyone to participate. And with that, I think we have a couple of minutes for questions. Thank you, everyone.
All right. How's everyone doing? How are you holding up? Yeah? Has this been good? I mean, I think there are more people here than when I started this morning, so that's a fantastic sign. And really grateful that you've all decided to show up here today. How many of you are members of Risc-V already? I love like some of you are like, yes, you know? How many of you have not yet joined Risc-V? Okay, have we got a deal for you? So the rest of the day, there is a slate of member meetings that are going on, ranging from community engagement and marketing and events and things like that, to technical deep dives and technical sessions to really kind of get to know some of the folks that are leading. You are welcome to stay and attend those types of discussions. You do need to become a member. Here's the deal. You can do that for free. All you have to do is go online, process through the membership document, and sign up, and you're ready to go. We also would like to invite you to stay for the rest of the summit. If you're here for Risc-V 101, we can get you a pass for the keynotes and expo. It's not a full conference pass. I don't think you get a t-shirt, but you can join us for the keynotes and expo portion, which is a great way to build your network and to kind of engage with your peers and make new friends. We're all here to make new friends, as well as have that, you know, family reunion with folks that we've been working with in the industry throughout our careers for many years. So invite you to stay and engage with that. And in Paris is having a stellar party later today, so you're going to want to definitely carve that out. If you haven't already stayed for the rest of the day, come back later for that. And you can register for any of that. I'm sure someone out there will be ready to help you with that. So that's what I have to say. Really excited about where Risc-V is going, how we are kind of really cementing the next stage of compute for the entire world, whether it's low power, lightweight devices, or the most high power, complex processing that is needed in data centers. We are really excited to share that journey with you and to kind of help grow Risc-V around the world. So thank you so much for coming, and let me know. Reach out to me specifically if there's anything I can do to help you become successful on Risc-V. So thank you.